So my name is Michael Knop. I'm a professor at ZBH, Center for Molecular Biology of the University in Heidelberg. I'm by myself a chemist by training, but by let's say experience, I'm mostly a geneticist with some let's say interest in basic cell biology, basic cell functions, and in methods development. Oh, when I started on the first day of my PhD thesis, I started working with yeast. Why? Pure accident. In those days, there was no internet where you can get information about what is studied in which lab, and I had an idea to go to a particular geographic location, and I just went to the lab where the professor could tell me the most interesting thing, which happens to be a yeast lab.
And what was the first positive experience you had when working with yeast, and what kept you working with yeast?
The first positive experience was that I, by myself, came up with an idea to do an experiment that gave me a paper within 9 months after starting my PhD thesis. So this gave me the positive feedback that you can actually do relatively quickly work that is actually published and internationally recognized. So first of all, the drawbacks is that you should not have the opinion that this is a simple and easy model system. It's as complex as any other model system in terms of being able to work at the forefront of research. That's the, yeah.
And so at the moment we are trying to establish a detection tool for short peptides, and when looking for an option how to do this, we came across the yeast mating receptor. Would you give us a quick introduction to such receptors and how the yeast mating system works? Why do they even have such receptors?
So the yeast mating system is basically a way to return from a haploid cell stage to a diploid cell stage as part of a complete sexual cycle. That is equivalent to sperm egg cell fusion. With yeast, the complication is that you can have situations with many different yeast cells in the same environment, and they have to establish some sort of communication in order to identify pairs that are willing to engage in mating. And there the pheromone receptor plays an important, basically key role. This receptor is a classical GPCR that basically is coupled to trimeric G protein coupled signaling. There is a MAP cascade, and everything is basically organized in a way that it's able to sense spatial cues in terms of pheromone gradients. Yes, so it's good in sensing peptides in the environment and also where they come from, how steep is the gradient, and so on, and then to couple this to the internal organization of the cell to polarize and to basically undergo cell-cell fusion.
Mm-hmm.
Yeah, I mean, you need to have coupled peptide with some sort of biological activity, right? And I think the only thing that is limiting is your fantasy and creativity, right? Yeah, I mean, right? I haven't thought about this, but I mean, there are many situations where protein interact with peptides, right? You can have bimolecular complementation, right? A short peptide that complements with the rest of the protein to get a functional enzyme. I think the first of these examples was simple RNAs that had done very early on, then whatever GST and so on, right? So you can come up, and then you can think always of evolving this luciferase, evolving these recognition sites to match with specific peptides, right? And then there's always the question about sensitivity, right? And there, yeah, I think there are probably more sensitive systems than GPCR. Yeah. Yes, so we did very early on in 2000 a directed evolution paper on DS red, which was a red fluorescent protein, which came out. As soon as it came out, I could get access to a synthetic gene, which in those days was not trivial. And then we did directed evolution, also had a paper on that, which convinced me and also showed me the problems of directed evolution, right? Because you have a huge search space, and you have to be clever enough to narrow it down and be more effective. And there it turned out that recombination strategies that are kind of adapted to a sexual recombination method is called DNA shuttling was very effective.
Mm-hmm.
So error-prone PCR is not really a tool for directed evolution, but it's just a way to generate mutations, meaning to generate genetic diversity, right? And evolution is basically has three components, and one is diversity, and one of the other is basically reproduction and then selection, right? And and in that case, I mean, this is a good way to make mutations, but then you have to handle these mutations in a specific way in order to optimize the search space, because you can only handle a certain number of clones maximally, right, depending on the screening system. But in yeast, it's probably 100 million. This is kind of the upper limit if you have a good assay, right? But if you do a combinatorial search space, I mean, you fill up the universe with alternatives, right? And so you have to be somehow clever, right? And there, just error-prone PCR alone is not sufficient. This is a way to get started, but yeah. I mean, DNA shuffling, the principle there is that you look for mutations that have a small advantage, which are relatively easy to find, and then you combine them together in a combinatorial way by using this recombination strategy, hoping to identify synergistic mutations. And this usually works quite well. It is still not useful if you need a breakthrough mutation, right? Because a breakthrough mutation is a mutation that basically initiates a certain ability, right? And so if you want to make a red fluorescent protein that is good for you, you should start with a situation where you have a very weak red fluorescence already. If you start with a green fluorescent protein, hoping to convert it to a red one, is almost impossible, because there you need a new chemical reaction. And there the search space is enormous, right? So you should start with a minimal ability, and then you can use DNA shuffling to improve this. And there are nice papers from Dan Dolphick also that explore this, also more theoretical, right? But yeah.
Mm-hmm.
So DNA shuffling is very effective because it mimics basic sexual reproduction, and yeah. I mean, this is basic evolutionary biology, right? If you have to have one mutation first in order for a second mutation to accumulate. So if you have clonal lineages versus recombination, right? And so this system will always lose against the DNA shuffling system where you recombine. But it can make certain optimization. It might work quite well if the search space is not so big, and you may be happy with a small improvement already. Yeah. And you should always be willing to talk about what you're doing in a way that people actually can understand it, right? This is the first thing, which is not always easy, right? Because sometimes, yeah. Yeah, I mean, you shouldn't miss an opportunity to talk about science, but then it's also a little bit on the individual preference, whether you want to engage more in science communication, right? Some people like it more than others, right? This is also, to be a good scientist, you don't need to be necessarily a good speaker or communicator, right? And so it's really individual preference, but we should have enough people in the scientific community, hopefully, who are willing to do that. Right, I mean, we participated in the Nacht der Forschung by an activity, which was this origami microscope, which we not did at the university, but at the German-American Institute here. Right, I mean, you're willing to do things if there's an opportunity, yeah, but I, as a scientist, I'm willing to do it, but it could be part of my job, but it's the individual's preference how active you want to be, right? And I think we have colleagues here who are doing a fantastic job in outreach, and they're much better than I. So it's probably more effective if they do it, and so on, right? Yeah. I mean, the best advice is always explain in family, friends, what you're really doing, right? So that they get a realistic concept what you're actually doing, right? This is key, right? The better you do this, the more effective it is. Yeah, and then of course, if you like writing journal articles, right? I mean, just proceed. I think there are many opportunities to publish this, right? There are Biospectrum, whatever. There are journals also in German, scientific journals. I mean, you have opportunities, right? It's more your interest, your skills, and your engagement that determines how far you go there, right? But if you want to tell someone something, right, then you should not. You should become active, right? And, yeah.